In this video, we'll be once again looking at the volume of revolution using washers or disks, such that we're rotating around objects or functions that are not the x or y axis. So in this case, we'll be looking at a quadratic function bounded by x equals 1, x equals 4 in the x-axis about the line y equals 5. So first off, we'll go ahead and graph this function to the best of our ability. There's x equals 1, there's x equals 4. We'll have the x-axis, which is again right about here. And then finally the quadratic, which is going to sit something like this, to the best of our ability. So we have this function here, and again you'll notice that the quadratic is on top of the x-axis the entire time, so that's how I would want to cut this particular space. The next piece that I'm going to go ahead and deal with is going to be me drawing the y equals 5 line. Now that y equals 5 line is going to sit somewhere up here, so that's the space that I actually have to rotate this object around. That's going to cause a little bit work for us to actually deal with. However, I'm going to go ahead and draw this space down here very carefully. I'm going to go ahead and draw this object here to the best of my ability. It doesn't have to be perfect, but it has to be at least relative to what I'm looking at. And then when I go to draw this y equals 5 line, you'll notice up here that if I'm going to go ahead and draw it exaggerated up here at y equals 5, that means that this is the location that this space is going to be reflected around. The distance from here to here and here to here should be the same as from the distance to here on this side, and over here on this side from here to here. And again, it should rotate about the same exact way that we would have seen it before. So what this looks like is actually a cylindrical object with a beveled shape curve cut out of the center. Okay, so there is the outer region, and here is our inner regions being cut out. So now this object it might be difficult to understand or realize exactly how it's supposed to be appearing, but the general idea is again that we're rotating it around that object, and again it looks like there's a drill hole in the center of it. We've got to figure out exactly what the volume of this object is. Now again, the rules don't change. I'm still going to go ahead and integrate. This way I'm cutting it so that my circular cross sections appear, and you'll notice that there is a center region cut out of it, so that I should deal with pi capital R squared minus pi lowercase r squared, and I should be cutting this in terms of x, because again, cutting these vertically. So it should be easy to identify the bounds being from 1 to 4, given that those were the functions x equals 1 and x equals 4, so that's where this location is to this location. The second thing I got to worry about is specifically how am I going to cut this thing in such a way so that I get capital R and lowercase r. Now, if I'm going to go ahead and take this thing out of the space, I'm going to redraw this circle over here. My capital R should represent this. Okay? Keep in mind, that should represent from here down to here. Now notice how I'm not drawing it up to this. I'm not drawing it up to this space right here, because this space right here was the mirror image of this one. So for us to go ahead and create an integral that's going to represent this rotated object that uses this region created by these equations, we must use these equations that represent this region, and therefore we must cut back into this space down here. Not the space up here, but this space down here where the original region actually appeared before rotation. So if I look back up here and I start here, what is the capital R going to be from this point down to the x-axis? Well, given that this y value is the y equals 5 location, that capital R, no matter where I draw it, should always be 5. In this case, y equals to 5, and therefore a y equals equation. So that's my capital R. My lowercase r, again, should be some region cut out of the center here, and my lowercase r, I'm going to label it here, should be r equals some other y value, but hopefully equaling to an equation, because again, you'll notice that if I cut this back to the interior function, not the exterior function, because this right here is the exterior function, but the first location of where the region object appears, that's going to be cutting it from this, again, axis down to the first location that I hit. So that right there would be the equation of my interior axis, my interior radius value. And that's going to be this equation right here. So again, it's going to be r equals to y, but not perfectly y in this case. It's going to be a distance that is reversed of this 5. So let's go ahead and draw this out here. Out here, this total distance is a total distance of 5. If this was the location I wanted to make to, that location right there is my lowercase r. This distance right here, and again, going up to this point, is actually a distance of y. That distance of y represents the height of this function here. So if I utilize these three pieces, these three lines, very clearly drawn, I'm going to go ahead and draw them more clearly here. That distance was 5. The distance from the axes to the actual region was r, the lowercase r. And then from that lowercase r to the axes, that's actually the distance of y coming from this equation. Okay? Which means that my lowercase r, if I were to create an equation out of this, is 5 equals to r plus y. So in other words, r, lowercase, is equal to 5 minus y, if I subtract the y over. So in reality, r is equal to 5 minus, and it's not going to be y because my function is in terms of x. I must have x squared minus 4x plus 5, which is the actual equation of that curved line. So this right here is my lowercase r. And you'll notice right here r equals 5 minus y. If we come back to this capital R, 5 minus my y, where my y value happens to be a distance of 0, should still satisfy the overall function. Now when I say y equals 0, I mean this line right here is the equation of y equals 0. So this r equals 5 is still satisfying 5 minus y. So over the time you'll see that there are a set of rotational axes equations that we can use, 5 minus y, depending on where our rotation axis sits in respect to the region we're actually looking at. So if I were to appropriately plug all this information in, I go from 1 to 4 of pi. My capital R is 5. Again, the capital radius is 5, the larger one, the most extreme one, furthest from the rotational axis, minus pi lowercase r is the distance from, again, the rotational axis to this location, which actually represents 5 minus x squared minus 4x plus 5, because that's the function, all squared, dx. So right there is the setup for the integral of the volume of this region rotated around the line y equals 5. And again, for this one to finish, you'd have to go ahead and first distribute this negative, combine like terms where appropriate, FOIL the square out, square the 5 out, and then integrate.